Hello, my name is Lene Majette, and today I'll be talking about the Euclidean algorithm. The Euclidean algorithm. The Euclidean algorithm, also known as the division algorithm, is a technique used to generate the greatest common divisor. Um, the Euclidean algorithm is also thought as the division algorithm, repeated until we get a remainder of zero. And forgive me, I said also known as the division algorithm. Rhythm is also known as Euclid's algorithm. The algorithm is named for the Greek mathematician Euclid. The Euclidean algorithm is one of the oldest and most recognized algorithms that is still in common use today. Meaning we still use it in different types of mathematics in different areas. So we're going to talk about the Elements. The Elements is a book that was written by Euclid. The Euclidean algorithm is written in Euclid's book, The Elements, and is in books 7 and in book 10. In book 7, it is seen in propositions 1 and in proposition 2. In book 10, it is seen in propositions 2 and in proposition 3. In book 7, the algorithm was created for usage with integers, while in book 10, it was constructed for the lengths of line segments and usage of real numbers. So we're going to talk a little bit more about book 7. Book 7, proposition 1 states that when two unequal numbers are set out and the less is continually subtracted in turn from the greater, if the number which is left never measures the one before it until a unit is left, then the original numbers are relatively prime. And relatively prime means they don't have another number that can divide into an equal. Book 7, proposition 2 then states to find the greatest common measure of two given numbers, not relatively prime. So pretty much we want to find the greatest common denominator, or the greatest common factor between those two numbers. A number that each number can divide into equally. That will divide into those numbers equally. Book 10, proposition 2 states, if when the less of two unequal magnitudes is continually subtracted in turn from the greater, that which is left never measures the one before it, then the two magnitudes are incommensurable. And in proposition 3, it states to find the greatest common measure of two given commensurable magnitudes. So, like we said again, we're still trying to find that greatest common number between those two numbers. We want to find the greatest common factor. So we're going to talk a little bit about the history behind the Euclidean algorithm. Although the Euclidean algorithm's name is given to Euclid, it is thought that the algorithm existed well before his time. It is thought that Euclid gathered results from previous mathematicians in his book, The Elements. So he just took other people's work and kind of put it in as his own. It is proposed that the book 7 originated from a text written using mathematicians in the school of Pythagoras on number theory. And Pythagoras was another great known scholar, mathematician. Euclid's algorithm was discovered independently by both in India and in China, used mainly to answer Diophantine equations in astronomy. By using the Diophantine equations combined with the Euclidean algorithm, the Chinese were able to make detailed calendars that we still use today. So now we're going to talk a little bit about the procedure and how we actually use the Euclidean algorithm. There are several uses for the Euclidean algorithm. It is primarily used to find the greatest common divisor between two integers, usually positive numbers. Please excuse the typo. Both of the numbers are usually positive numbers. The algorithm is written as A equals BQ plus R, where A is the dividend, B is the divisor, Q is the quotient, and R is your remainder. To find the greatest common divisor, or the GCD, between the two integers A and B, where A is the larger of the two integers, the goal is to find the quotient such that the remainder is equal to 0. So we're going to keep repeating the same steps over and over again until we get a remainder of 0. Once we find that, then we find out what our greatest common divisor is. If the GCD is equal to 0, the integers are said to be relatively prime. So here's example 1. We're going to go through an actual equation, and we're going to find the GCD using that number, using the algorithm. So it says find the GCD of 17 and 23. First, we have A is equal to BQ plus R, and we're going to use 17 and 23. That is going to be our A and our B. We're going to put A as 23 and B as 17. We usually want our bigger number to be our A, our smaller number to be our B. Thus, our equation is going to be 23 is equal to 17Q plus R. And now we need to see how many times B can go into A. So we need to find how many times our 17 can actually go into 23. And if you look at it, we know that 17 can only go into 23 one time. Oops, sorry. So 17 can only go in there one time. Now we place R with the remainder. So we say 17 times 1 gives us 17. So we need to fill in and find out 17 times 1, but plus what is going to give us that 23, which is our remainder. So we know that 17 times 1 is going to give us 17. So we need 6 more. We're 6 away, so we need plus 6, which will give us our 23. So now we've replaced A. So now we have our R, which is 6. Now we replace A with B, and we replace B with R. So we're going to take we're going to replace A with B, so we're going to move 17 to the outside, and we're going to replace B with R. We're going to take our remainder right here and put it where our B term was, and then we're going to repeat the whole process again. So now we have 17 is equal to 6Q plus R, and again we're going to repeat by finding out how many times B, which is now 6, goes into 17. Once we find out what our Q is, then we'll be able to find out what R is. So now looking at this, 6 goes into 17. So I'm going to ask my daughter, she's behind the camera. Ayana.
Yes.
How many times does the number 6 go into 17?
2.
It goes in there 2 times. Good. So we get 6 times 2. So when I get 6 times 2, I need to figure out what my remainder is. So I have 6 times 2. 6 times 2 is what, Ayana?
12.
12. So what would R be in order for us to get 17?
5.
Good job. So that means our R is our remainder, which is going to be 5. Good job. And everybody, she's only in the 7th grade, so she's doing very well right now. We continue the process until we get a remainder of 0. And is R equal to 0, Ayana?
Yes.
Is R equal to 0, Ayana?
Oh, no.
It's equal to 5. It's okay. So we need to repeat the process again. Again, moving 6 into the A position, R into the B position, and this time we've already got it spelled out for us. 5 times 1 equals 5, plus 1 gives us our 6. Still in our R position, we still do not have a 0, so we have to continue the process. We go again. 5 is equal to, we move 5 over to the A position, we move 1 over to the B position. This time we have 1. 1 goes into 5 times, plus now 0, which is required. So now we have R is equal to 0. We stop the process. and the number located in the B position is our GCD. So the number in the B position is 1. Therefore, the GCD of 17 and 23 is going to be equal to 1. Hope I didn't confuse any of y'all too much with that. So now we want to do the Euclidean algorithm backwards. We're going to do the Euclidean algorithm can also be used backwards to find a linear combination where some form of integers a and b, there exists a s and a t, where as plus bt is going to be equal to the GCD of a and b. So using our previous example, we're going to take as plus bt and make it equal to our GCD of that a and b. And as we had before, a was 23, b was 17, our GCD, as we just figured out, was 1. So we're going to have 23s plus 17t is going to be equal to 1. And we're going to use that equation to find an s and a t such that this equation becomes true. From the previous example, we're going to look at the next to the last line. 6 is equal to 5 times 1 plus 1. And we're going to rearrange the equation such that the GCD is the remainder. Such that it equals the GCD, or that it equals our remainder. So the GCD of 17 and 23 is 1. So the equation will go as follows. We're going to have 1. Because we're going to move this, our 1 is going to be by itself, so that 1 is going to be equal to 6 times 1 minus 5 times 1. Even though we don't see that 1 right there, we're understood 1 being multiplied beside that 6 right there. From there on, we go to the lines above to the next line, replace the integer not in the equation. So from line 17 equals to 6 times 2 plus 5, we're then going to solve for the remainder, which is the 5, which is going to give us 5 is equal to 17 times 1 minus 6 times 2. And that's just us moving the equation around. So now we have 1 equals 6 times 1 minus, and we're going to replace what 5 is equal to with this equation right here. So we're going to put all of this in for 5, substitute in for 5, and leave our 1 on the outside. We then distribute and combine like terms, giving us 1 is equal to 6 times 1 minus 17 times 1 plus 6 times 2. Giving us now 1 is equal to 6 times 3 minus 17 times 1. And if you actually work this out, it is true. 18 minus 17 will also give us 1. But that's just the beginning of the equation. We're going to hurry this along because I think I'm running out of a little bit of time. So, from the previous example, I have it all written out for us. We're going to do the Euclidean algorithm backwards. So we're starting with 23 equals 17 times 1 plus 6. We have 17 equals 6 times 2 plus 5. 6 equals 5 times 1 plus 1. Then we have 5 equals 1 times 5 plus 0. And our GCD, like we said before, was equal to 1. So now we're going to start working it out backwards on this side. And like I said, we're going to start from not this line, but this line right here. And we're going to rearrange our equation. So we rearrange our equation. 1 is equal to 6 times 1 minus 5 times 1. We go back to our next line, rearrange this line so that we make it equal to the remainder. And we're going to take that equation and stick it back into the equation. So we have 1 is equal to 6 times 1. We replace 5 with our new equation, 17 times 1 minus 6 times 2. And we're going to distribute this 1 into our, equation. And then we're going to combine like terms. Once we do all that, we have 1 is equal to 6 times 3 minus 17 times 1. That is true. It's going to give us 1. 18 minus 17 gives us 1. We still have one more line left up here. And we're going to go back. And this time we're going to solve for our 23. So solve for 6. We're going to rearrange it so we can put it in for 6. We put it